ChatGPT, Claude, Gemini. They're brilliant, but let's be honest. They know nothing about your business. Ask them something nuanced about your internal docs, meeting notes, onboarding documents, or client history. They fumble, or worse, hallucinate with confidence. But here's the thing. What if you could build your own AI assistant? One that actually knows your business. No training, no fine-tunings, just clear, concise answers. From your data, your model, completely private and deployable. By the end of this video, you'll have a business-aware AI assistant that knows your business inside out and runs entirely on your own stack. By the way, if you're new here, I'm Fraser Dorado, and I've been building large-scale enterprise software for almost a decade. And now, through my AI and automation agency, I help businesses build and scale real-world AI systems. As part of that mission, I share the same frameworks and learnings here so you can apply them yourself. So at a high level, here's what we are building. An AI assistant that actually understands your business, powered by your own data and running completely privately. We'll combine three key parts. An ingestion pipeline that processes your company's documents, like PDFs, Word files, text notes, and stores them in a searchable knowledge database. An open source deployable LLM that acts as the AI agent, and a clean front end, a ChatGPT-like UI where you can query your company's knowledge. You'll see exactly how all of this comes together when we walk through the app's architecture. But first, let's look at why general-purpose models like ChatGPT or Claude fail the moment you ask them about your business. Models within ChatGPT, Claude, or Gemini aren't connected to your internal world. They're trained on the open internet, not your internal documents, your client notes, or that humongous SharePoint full of product specifications. So when you ask, what are our latest finalized product specifications? Or what's our most recent client's business about? It either says it doesn't know or it guesses. Now sure, context windows are getting larger, but there's still a limit to how much you can fit in. And even if you stuff the context to its max, it's like asking a model to find a needle in a haystack. Sometimes it hits, but often it misses. To bridge the gap, OpenAI and Anthropic introduced something called projects or artifacts. They let you upload files, keep memory, and give the model context across chats. Basically a mini workspace for your data. Think of it as ChatGPT with a working memory for a single topic or a theme. Claude does something similar, automatically using retrieval once your project grows too large for the model's memory. That's great if you just got a few documents or a small team. But here's the catch. It still runs on their servers under their rules. There's no true privacy unless you're on enterprise level plans. And still, do you really want to hand over your company's IP that easily? Think about that for a second. And on top of that, you have zero control over how retrieval actually works. You're also capped at around 40 files in ChatGPT, maybe 100 in Claude, and there's still no way to customize how your data is indexed or queried. Soon you realize the generic setup they provide just isn't good enough for your business. The answers feel off, incomplete, sometimes so bad you end up looking up the information yourself. And that's the real problem. If you want an AI that actually knows your business, one that doesn't fumble the moment your data or your team scales, you need something more robust. You need a system that can securely retrieve, reason, and respond from your data under your control. That's where a custom, private, RAG AI business assistant comes in. It combines retrieval, context assembly, and your own local or hosted LLM, giving you full visibility, privacy, and integration. Now let's look at what's under the hood, the architecture that powers a truly business-aware AI assistant. We've got 6 main components that make up the full system, starting from your data and ending with the chat interface. First, we have our data sources, where the truth lives. This could be your local storage, Google Drive, SharePoint, Notion, or Confluence. Basically anywhere your company knowledge is sitting. PDFs, Word documents, text files, you name it. Next, we have the ingestion and indexing pipelines. This is where we parse the documents, clean up the text, split it into smaller chunks, generate embeddings, and store everything in a database. For this demo, we'll be using PostgreSQL with a vector extension as it's simple and reliable. Then comes retrieval. When you ask a question, this layer searches the vector store to pull the most relevant snippets. That's what makes your AI assistant aware of your business instead of just guessing from general knowledge. After that, we have the LLM orchestrator, or you can call it the AI agent. This is the piece that builds the actual prompt for the model. It takes your question, adds the retrieved snippets, and wraps everything in a bit of instruction, basically giving the model the context it needs to think. Next is the model itself. You can run it locally or call a hosted provider, totally up to you. Local models like GPT open source keeps everything private, while hosted ones like GPT-4o or Claude give you more raw power, but of course your data leaves your environment. Either way, the workflow stays exactly the same. And finally, we have the app, just a clean, lightweight chat interface for users to talk to the assistant. It sends the question, gets a response, and shows the answer along with the document sources right inside the chat. Now that we've got a clear picture of what we are building today, let's break down the logic behind how this actually works. We'll start with a simple implementation, just enough to see how the pieces connect, and in later videos, we'll go deeper into scaling more advanced retrieval pipelines. I'll walk you through the exact flow in a simple Jupyter notebook. Once you see the logic, the app will make complete sense. And with that, let's dive in. We're going to start by installing a few dependencies, which I've already pre-installed, but feel free to pause the video and install these dependencies as they are required. Throughout this notebook, we're going to use Llama Index. For those of you who do not know what Llama Index is, it's an open source framework for building applications powered by LLMs. They are especially known for their data connector ecosystem, so it's really good for building data ingestion, indexing, and retrieval pipelines. We're going to start with setting up the Ollama embedding. We're going to point it to the embedding Gemma 300 million parameter model. It's an open source model provided by Google for embedding purposes. Right? It points to the Ollama hosting URL. Let's run that. Next, we're going to use a method, right, that you can call the getText embedding, and we're going to just pass a random piece of text in there, and we're going to look at the vector length. So embedding Gemma model from Google provides a dimension of 768, and you're going to see that here. As you can see, you got a vector length of 768, and how do these vectors actually look like, right? They're represented by these numbers, and those numbers portray how this piece of text kind of looks like in the embedding space. Next, we do a query embedding. So we pass a random query, again, just another string of text. The implementation of get query embedding and the get text embedding is similar in this case, but there are scenarios that it can be different. Let's run this. As you can see, we got the same vector length again, and dimensions representing that piece of text. Then we're going to set up the Ollama model, and we're going to make a quick completion call to it, asking it what's the capital of France, just to make sure everything is up and running. Fantastic. It tells you the capital of France is Paris. Next, we're going to set up the PG vector store. Here I've put in a few notes on the dimensions and its variations, by the way. So the lower dimensions that you go, the faster is the retrieval, but lower is the accuracy. Just remember that. We're going to set up the PG vector store. This is again provided by Llama Index. And we're going to set up the relevant parameters where we have a database called a vector database. The host is localhost. Password is change this password. Please do not use this password. It's just for demo purposes. We're going to set the port, the user as admin. We've created a table called business docs, and the embedding dimensions is 768. We're going to run that. Awesome. Next, we're going to use PDF loader. So PyMovePDF is one library that's quite good at this, but there are many others. I think there's PyPDF as well. Choose one that fits your use case. They all pretty much work the same way. And we're going to load this file into this loader. So we have a terms and condition PDF. This is also the PDF we're going to use throughout this whole demo. So we're going to load those documents. So let's run this. Next up, we have the sentence splitter. We're going to create an instance of the sentence splitter where we're going to pass the chunk size and chunk overlap. This is essentially the size that we're going to split the documents into. So the chunks that will be created, they will be created of a size 1024, and that's going to be an overlap of 256. Now this chunk overlap is quite important because when we create the snippets or these chunks, right, they might not always split the document in a correct manner. So it might split the paragraph halfway before it was actually completed. and it might be relevant part of that context. So you always want to keep an overlap where there is some part or relevant part of the previous chunk in the new chunk. And this way, when you do a vector search, you get all the relevant documents that might be related to each other. So let's run that. And then we're going to create the actual chunks. We're going to use the text parser to split the documents, and then we're going to add it into the chunks array. So let's run that. Awesome. Next, we're going to create the text nodes. Right? These are nodes that contain the chunks and its metadata. So as you can see here, we're creating an instance of a text node. We're passing the text chunk. We're also passing in the document metadata, and we are appending those to the nodes array. Let's run that. Great. Then we're going to loop through the nodes, and we're going to create embeddings for all the contents and add those embeddings back to the nodes as well. Let's run that too. Now we'll add all those nodes to the vector store that we created earlier. Great, they have been added. Now we're going to create a simple query string. In this case, can the company use clients for testimonials? That's the question, right? We're going to get the query embedding for that. Fantastic. And then we're going to create a vector store query. So in that vector store query, we pass the query embedding, the similarity top k, and the mode, which is default. In this case, similarity top k indicates that it should return the top 5 most similar content. Let's run that. We then pass the vector store query to the vector store to get the query result. So let's run that. And this is the content that was retrieved. We are also going to create a node with scores. This is important when we create the VectorDB retriever that you're going to see in the next block. But essentially every result that is retrieved, it has a score attached to it. And that score tells us how relevant a piece of chunk is to the query that was requested. So let's see that in action. To do that, all we need to do is loop through the query results, as you can see here, and get the score out of it. Let's run that. Now we're going to set up a VectorDB retriever, which extends from the base retriever from llama index. We're going to set up an init method here, which initializes the vector store, embedding model, query mode, and similarity top k. It also has a retrieve method in there, where it's going to do exactly what we did above. It's going to embed the query. It's going to create a vector store query, and it's going to create nodes with scores. So let's run that. Fantastic. And then we're going to create the VectorDB retriever. We're going to pass the vector store, the ollama embedding, the query mode, and the similarity top k. And then we're going to use the retriever query engine from llama index, where we're going to pass the retriever and the LLM. The LLM is passed here in order to synthesize the response. So once it gets the documents that are similar or relevant to the query, the LLM decides how it should portray the response. Let's run that. Again, we're going to use a query string. We're going to pass that query string to the query engine. And just like that, you have a response. Pretty interesting, right? That's it. Now let's take a look at how this ties together in the application. As you can see here on the left, to keep this demo focused, I've built a lightweight Next.js frontend, so you won't have to spend time on the UI code here. Our main focus will be the backend flow and how everything connects behind the scenes. We're going to start with the init.sql file. This file creates the vector extension if it does not exist. It creates a simple table as well called business docs. And this table contains an ID, an embedding, content, and a created at field. And finally, we create an index on the business docs table using HNSW. For those of you who do not know what HNSW is, it's an algorithm used for approximate nearest neighbor search in high-dimensional vector data. This file is then going to be picked up by our Docker Compose file, which we're going to look at next when it creates an instance of pgvector. Next, we have a very simple Docker Compose file. Here we have a pgvector image, right? We gave it a container name. We set up some environmental properties. Again, please do not use this password. It's only for demo purposes. We set up the ports and we set up the volumes. Next, let's look at how the server looks like. In the server file, we load the environmental properties. We set up a basic logging configuration. We then go on to set up the LLM, and we're going to talk about that in a bit. But here we pass in the model name and the base URL, which is controlled by the environmental properties. And based on whether we want to call the cloud hosted version or the local hosted version, all we need to do is change the model name and the base URL, which I think is pretty cool. Then we're going to set up the lifespan. This basically initializes the reg system on startup and sets the query engine as well as registers the tools. Then we're going to create a simple app, a fast API app, where we pass the title, the version, and the lifespan. We set up the middleware that's required. And lastly, create a simple API/chat endpoint, which is a server-side events endpoint. It's going to stream responses back to the front end. If you look inside there are a few log statements which can be ignored for now, but what you should pay attention to is the line 76, where you convert to OpenAI messages. Essentially what this method does is that it takes the messages from the front end, that's received from the front end, converts them to OpenAI messages. It's a format in which OpenAI SDK expects the messages to be. Look at that function in a bit. We also create a streaming response, which calls the LLM.stream with AI SDK protocol. This is in the LLM class, and we'll walk through it as well. It essentially converts back the messages that we receive from the OpenAI SDK into the message format that the front end expects. And it streams this as the events come to us, or as the events are given out by the SDK or by the LLM. You're also required to set a few response headers, and this is a requirement from AI SDK. And AI SDK is the framework that we use on the front end to give us the ChatGPT-like UI that you will see in a bit. And finally, we return a response. And with that, we are done setting up the endpoint. Let's now take a look at the LLM class. Okay, the LLM class is basically an abstraction over the OpenAI SDK. And if you've seen my previous videos on automating data entry or chatting with your database, you'll see me use a similar pattern where I abstract out the implementation details with an LLM class, because then it allows me to change the implementation without having to impact the rest of the code, right? So if you look into this class, you'll see that we set up the model name, base URL, and options, which are then passed on to the OpenAI client. We also have a method to register tools, where we pass in the name, handler, and definition. Handler is essentially the method that executes the function. And then we have a method to stream with AI SDK protocol. There we pass in the OpenAI messages, we pass in the model name, the tools, and tool handlers. And this essentially streams the response back to the UI. With that, let's take a look at tools.py. In the tools file, we have a method to set up the query engine, which you have seen that we did in the lifespan while setting up the server. We also have the search internal docs. This is the tool that will be passed to the LLM, and if the LLM requires to search documents, it will use this tool to retrieve the data. As you can see here, it uses the query engine. It passes the user query to the query engine. It gets the response, formats the response into an answer and sources, and returns that back to the LLM. Now let's take a look at the tools definition file. Tools definition here is nothing but how you describe a tool to the OpenAPI client. The way you do it is you define the definition, where you provide the type, which is a function. You provide the name of the function, a description as to what the function does, the parameters that are required, that in this case is the query, and then you mention that the query is required. What the LLM then does is, with this description, it then knows that it needs to create an input parameter called query, which will then be passed on to the function to be executed. We also have a method here for registered tools, which again you saw that we initialized during a lifespan while creating the app. All this does is that it registers the name, the handler, and the definition of a tool. Next, we're going to look at the utils file. The util file handles the conversion of messages from front-end to back-end and back-end to front-end. There's two methods in here. One is to convert the messages to OpenAI messages. All it does is it takes in the front-end messages that are received and it converts it in a format that OpenAI expects. You can find this format in the documentation of OpenAI SDK, so please do have a look at that. And second, you have the Stream with AI SDK protocol. And essentially what this does is it converts the OpenAI messages back to the format that the front end expects. Again, the format is available on the AI SDK documentation, so please do read through the documentation. It's quite verbose and well written. Lastly, we're going to have a look at the init.py. The init file essentially puts together everything that we have seen in the Jupyter notebook. So if I open my files on the left, you will see that I've created multiple components of the things that we saw in the notebook. And I've created chunkers, I've created an embedding component, a loader component, pipeline, retriever, and a vector store component. The reason I did this is in order to productionize this a bit. And you can change each component or the implementation of each component without affecting the overall code. Now, if you look at the initialize reg system method, right? This is what we initialize at the start of the application in the lifespan. What it does is it initializes the ingestion pipeline. It sets the data directory, the LLM model that is required to synthesize the response. It creates an instance of the LLM. It then sets up the reg query engine, which is then used by the search internal document tool that we saw earlier, right, to retrieve the right content. And finally, this is then returned back to the instance. And that's it. A lightweight setup, just enough to run comfortably on your laptop today, but flexible enough to deploy and scale when you need to. With that, it's time to see this in action. We'll run our business assistant and watch how it handles actual data. I've already indexed a few documents for a dummy company I created, so the assistant has a small but realistic knowledge base to work with. What's fascinating is that the assistant not only has access to the documents I provided, but also its general training knowledge. So let's ask a question and see how it responds. Does our company testimonials? As you can see, it's thinking about the message. It's running an internal search. It now fetched all the snippets that are relevant to the query or the user query that I provided. And it gives me a response saying that the policy does not automatically allow the use of client testimonials. Momentum Growth partners may only use a client's name, likeness, or testimonial for marketing after receiving prior written consent from the client. The client can grant or withhold that consent at their discretion. Now you're probably wondering if this is accurate or not, so let's take a look at the terms and conditions PDF that was ingested. If you look at this, here's the testimonials and publicity section. And as you can see, it's exactly as the assistant provided us. Now let's try a different question. What is our company's refund policy? So it's doing an internal search again. And if you open up that tool, you'll see that the query that was created, right, that was passed to the vector storage, and the result that was synthesized. And that's the result that we can see here. Let's look if this is actually even accurate. As you can see here, it is indeed correct. The AI was smart enough to find the right information, right, and synthesize the correct response. And that's it. What's powerful here is that you can swap out every layer, the vector database, the embedding model, even the LLM, and the system stays the same. So whether you're using a proprietary model like GPT-4o, which gives you more reasoning power, but means giving up a bit of your privacy, or an open source model like GPT open source, the logic does not change. It still retrieves reasons and response entirely from your own data. And that's the beauty of the setup. It's fast, modular, and completely private. So at this point, you've seen how to take your company data, whether that's internal documents or client notes, and turn it into something intelligent. An AI assistant that actually understands your business. Before today, tools like ChatGPT or Claude could only guess at your internal context. Now you've built a private system that retrieves actual answers, reasons from your data, and stays fully under your control. This is the shift that's happening right now. From using public AI tools to deploying private AI infrastructure that becomes part of how your business operates. And this foundation opens the doors to everything that comes next: automations, integrations, and full-scale AI operations tailored to your workflow. And if you're a business looking to deploy something like this, that's exactly what I help with. You can reach out using the links below to get a version tailored to your setup. You now understand what it takes to make an AI assistant that truly knows your business, not just imitates it. If this walkthrough gave you a clear picture of how to create your own business aware AI assistant, drop a like. It tells me you want more practical system level builds like this. And if you want to keep learning how to build AI systems that actually work in the real world, hit subscribe so you won't miss the next one.